All right, welcome back to the deep dive. Today, we're taking a look at something that's really at the cutting edge of AI, and it's the question of how you teach artificial agents to play those really complex, strategic games where it's not just about reacting, it's about anticipating what your opponent is going to do.
Yeah, and that's a whole other level of complexity, isn't it?
Absolutely. We're talking about games where there's a clear leader and a follower. It's like a chess match, right? One player makes a move, and then the other player has to react to that. But the first move sets the tone for the whole game.
I see, so like a chain reaction almost.
Exactly. And that's what makes this particular research so fascinating. The paper we're diving into is called Imitation Learning of Correlated Policies in Stackelberg Games. A mouthful, I know, but bear with me.
Okay, breaking it down. So Stackelberg Games, that's this leader-follower dynamic we're talking about. What about the imitation learning bit?
That's the heart of it. See, traditional AI training often involves agents learning through trial and error. They try different things, get feedback, and adjust their strategies. But what if you want them to learn by watching experts? Like, how do you translate that human expertise into something an AI can understand and replicate? That's where imitation learning comes in. And correlated policies refers to agents that can anticipate and adapt to each other's actions, not just reacting, but predicting.
So this paper is basically about getting AI to learn complex strategic interactions by watching how the pros do it, specifically in those leader-follower type scenarios.
Makes sense. Exactly. And it's a pretty big deal because even existing methods, the ones specifically designed for those correlated policies, they struggle in these Stackelberg games. It's because of that inherent asymmetry, the leader and follower not being on equal footing, that throws things off.
Right, because their decision-making happens at different points in time.
Yeah.
It's not a level playing field.
Exactly. And as the paper points out, even if you try to treat the inactive agent as just doing nothing during their turn, you're missing the point because they're very in action. The fact that they're waiting to see what the leader does, that influences the game. It's strategic.
It's almost like a silent pressure, just waiting to react.
Yeah, a bit like that. And current methods, they often result in either agents that act in a completely disjointed way, or they become so computationally heavy that they're just not practical for anything beyond the simplest scenarios.
I see. So we need something more robust, something that can handle this kind of complexity.
And that's where the authors of this paper come in. They've developed something called the Latent Stackelberg Differential Network, LSDN for short. It's a bit of a mouthful.
LSDN. All right. I'm intrigued. What is it?
Okay, so imagine instead of looking at individual actions at each step, you look at the entire trajectory of the interaction, like you're tracing the path of a dance, not just focusing on the individual steps. And you do this in what's called a latent space, a sort of hidden representation of the game.
Okay, so we're moving away from the granular actions and taking a more holistic view of the interaction.
Exactly. And to model this trajectory, they use something called a multi-output geometric Brownian motion, MOGBM. It's a way of modeling how multiple things change randomly over time while also being related to each other.
Oh, that's interesting. So like how two dancers' movements are both influenced by the music and also by each other. They're kind of interlinked.
That's a really good analogy. And the beauty of using MOGBM is that it allows the LSDN to disentangle what's being caused by the agents themselves, their strategic choices, versus what's just the randomness of the environment. It separates those two things.
Ah, I see. So it's like saying, okay, the music is the environment, but the dancers' individual styles and how they respond to each other, that's the strategy.
Right. And this separation is really important because it means LSDN can learn these correlated policies simultaneously without having to use those adversarial training methods that a lot of other approaches rely on.
And why is that a good thing? What's wrong with adversarial training?
Well, those methods can be really unstable. It's like trying to teach two dogs to share a toy by constantly putting them in competition with each other. They might learn, but it could also get pretty chaotic.
Oh, right. Yeah.
Yeah.
So LSDN is more like a gentle guiding hand.
It is, and that makes it much more efficient and reliable. And the paper backs this up with some really impressive results. They tested LSDN in a variety of scenarios, from those classic game theory problems like the iterated prisoner's dilemma, where you have to decide whether to cooperate or betray your opponent.
Ah, yes, the classic dilemma. I always end up betraying, just in case.
Well, maybe the AI can teach us a thing or two about cooperation, but they also tested it in more complex, simulated environments, like those multi-agent particle environments.
So they really put it through its paces, huh?
They did, and it consistently outperformed existing methods, both in terms of how well it could replicate the expert's behavior and how quickly it could learn. It was better at capturing those subtle nuances of interaction.
That's really impressive. So this LSDN seems like a huge step forward in imitation learning, especially for these leader-follower scenarios.
It is, and to understand why this is such a big deal, it's helpful to take a step back and look at how we got here. The history of multi-agent learning, if you will. A lot of the early research focused on what are called Markov games, where all the agents are making decisions simultaneously. It's like a multiplayer video game where everyone is acting at the same time.
Got it. So a more symmetrical kind of interaction.
Exactly. And in these scenarios, you can analyze how often certain combinations of states and actions occur together. It's called the joint occupancy measure. And methods like Codale have shown some success in these kinds of games.
But that doesn't quite apply to Stackelberg games, right? Because of that turn-based structure.
You got it. In fact, the paper even has this really helpful figure 1 that visually explains this. When actions are simultaneous, you can look at this combined snapshot of everyone's state and actions to get a sense of the overall behavior. But in a Stackelberg game, the leader's action sets off a whole chain of reactions. It's not simultaneous, so that idea of joint occupancy measure breaks down.
It's like trying to analyze a conversation by just looking at a transcript of everyone speaking at once.
Yeah.
You lose the flow, the back and forth.
Right. And that's why a lot of traditional methods that rely on the assumption that agents are acting independently, they just don't work well here, because the follower's best response is directly tied to what the leader does. It's like a dance where the follower has to anticipate the leader's next move.
And that's where correlated policies come into play, right?
Right.
Taking into account what the other agent is likely to do.
Exactly. And Codale, which we mentioned earlier, it was an attempt to do this, but it still struggles in Stackelberg games because of that fundamental asymmetry. It's like trying to predict the next move in a chess game without knowing whose turn it is. You're missing crucial information.
Yeah, context is everything.
It really is. And on top of that, many existing methods face this trade-off between being able to handle really complex situations, those high-dimensional environments like what a robot might encounter, and being stable enough to actually learn effectively. They either struggle with the complexity or they become unreliable.
Right. So it's like you need a method that can handle both the complexity of the game and the intricacies of that leader-follower dynamic.
And that's where the key insight of this paper comes in. They shift the focus away from trying to directly match those problematic joint occupancy measures and instead look at how the leader's action directly influences the follower's next state. It's like looking at the ripple effect of that initial stone thrown into the pond.
Oh, I like that analogy. So instead of trying to analyze the chaotic splashing, you look at the pattern of the ripples to understand how the stone was thrown.
Exactly. And they formalize this by reformulating the idea of the occupancy measure specifically for Stackelberg games. Instead of a simultaneous snapshot, they look at a sequence. The state at a given time, the action taken, and the resulting state in the next step. This captures that cause and effect relationship.
So they're explicitly modeling that sequential turn-based nature.
They are. And the goal of imitation learning then becomes minimizing the difference between this learned sequence distribution and the distribution of sequences demonstrated by the expert.
So it's all about getting the AI to generate sequences of states and actions that look as close as possible to what the expert would do.
Precisely. And they provide a theoretical justification for this approach with Theorem 1, which basically says that if your simplified representation of the game state captures all the essential information, then minimizing this difference in that simplified space will also keep the difference in the real complex game state within reasonable bounds. It's a really important theoretical foundation for their method.
Okay, so we've talked about the motivation and the theory behind it. Now, can we dive a bit deeper into the LSDN architecture itself? How does it actually work?
Absolutely. So as we mentioned, LSDN models the interaction as shared trajectories in this latent space. And it uses the MOGBM, that multi-output geometric Brownian motion, to model these trajectories. It's like tracking the movement of two particles that are both influenced by their own internal dynamics and by random external forces.
I'm visualizing those two dancers again, moving in sync, but also having their own individual flair.
Yeah, it's a good way to think about it. And the drift component of this Brownian motion represents the agent's learned policies, their strategies, while the diffusion component captures that environmental randomness, the unpredictable elements.
So it separates the intentional movement from the random noise.
Exactly. And they design this drift component in a really clever way. It's broken down into separate parts that model the leaders and the followers' individual contributions to how the game state changes. And they embed this whole thing within a variational framework.
A variational framework. Refresh my memory. What's that all about?
It's a way of dealing with uncertainty and learning complex probability distributions. Imagine you have an initial guess about how something works, and then you update that guess based on the data you observe. That's the basic idea.
So they start with a kind of prior belief about how the leader and follower interact, and then refine it based on the expert demonstrations.
You got it. And crucially, they share the diffusion component between the leader and follower models. This helps ensure that the learning process stays stable.
So it's like saying that both dancers are influenced by the same music, even though they might interpret and move to it differently.
That's a great way to put it. And then to actually translate these learned policies into actions that the AI agents can take in the game, they use an inverse dynamics model. This model takes the state at one point in time and the state at the next point in time and tries to figure out what action must have been taken to get from one to the other.
It's like working backward from the finished dance routine to figure out the individual steps.
Exactly. And the entire learning process is guided by optimizing this thing called a variational lower bound, which balances how well the model reconstructs the observed data with how well it adheres to those initial prior beliefs. It's a common technique in this kind of modeling.
So it's making sure that the AI isn't just blindly copying the data, but also incorporating some level of prior knowledge and structure.
Right. Now, to really test their method, the researchers conducted a whole battery of experiments. They compared LSDN against several other state-of-the-art methods, including MAGL and CODALE, which they cleverly adapted for the Stackelberg setting. They even tested against a specialized version of the Stackelberg decision transformer.
So they really wanted to see how LSDN stacked up against the best of the best.
They did. And they tested these methods on a variety of games, including the iterated prisoner's dilemma, Le Duc Hold'em, which is another game with this leader-follower structure, and the multi-particle environment, which is a more complex simulation with multiple interacting agents.
So a good mix of deterministic and more unpredictable environments.
Exactly. And the results were pretty convincing. In both the iterated prisoner's dilemma and Le Duc Hold'em, LSDN consistently outperformed the other methods. It was better at learning those correlated policies in those deterministic games, meaning it could really capture the strategic interplay between the leader and the follower.
So it was really good at figuring out the dance between the two players.
It was. And even in the more unpredictable multi-particle environment, LSDN performed really well, especially when it came to replicating the specific interaction strategies demonstrated by the experts. They used a measure called the Jensen-Shannon divergence to compare the patterns of movement, and LSDN was much better at mimicking the experts' behavior than the other methods.
So even when there was more randomness involved, LSDN was still able to pick up on the experts' subtle tactics.
It was. And this suggests that using the MOGBM, that Brownian motion model, is particularly helpful for handling the kind of uncertainty we'll find in those more complex environments.
It's like the MOGBM helps the AI navigate those choppy waters and still keep track of the dance steps.
Exactly. And they also did an ablation study where they removed the MOGBM from LSDN just to see how important it really was.
So they wanted to isolate the effect of that particular component.
They did. And they found that while the system still performed reasonably well without it, it was definitely less effective. It lacked that structured way of dealing with the environmental uncertainty. So the MOGBM is definitely a key part of what makes LSDN work so well.
It's like taking away the music and asking the dancers to improvise. They might still be able to dance, but it wouldn't be the same coordinated performance.
Exactly. And they even visualized the agent interactions in the multi-particle environment. And you could clearly see that the agents trained with LSDN moved in a way that was much more similar to the expert demonstrators than the agents trained with the other methods.
So visually, it was evident that LSDN was doing a better job of capturing the essence of the expert's behavior.
It was. Now, taking all of this into account, what are some potential future directions for this research? What kind of novel notions come to mind?
Well, one really interesting avenue would be to explore how we could give these AI agents a kind of rudimentary theory of mind. Instead of just mimicking the actions, could we extend the LSDN framework to try and understand the intentions or the beliefs behind those actions?
That's fascinating. So the AI wouldn't just be learning what to do, but also trying to figure out why the expert did what they did.
Exactly. And that could lead to some really interesting advancements. If the AI could learn representation of the expert's reasoning process, it might be able to generalize much better to completely new situations, or even interact more effectively with opponents it hasn't encountered before. It would be like going beyond just copying someone's dance moves to understanding the emotions or the story they're trying to convey through their dance.
That's a great analogy, and I can see how that could be incredibly valuable in a lot of real-world applications. Imagine a robot that can understand a human's intentions and provide assistance that's truly helpful and intuitive, or an AI that can participate in negotiations and anticipate the other party's goals and adjust its strategy accordingly.
Exactly. And while giving AI full-blown human-level theory of mind is probably a long way off, incorporating some basic forms of belief modeling into a framework like LSDN seems like a really promising area for future research. It could be a big step towards making AI agents more adaptable and intelligent.
Absolutely. Another thought I had was the paper focuses on two-player Stackelberg games. What about extending this to scenarios with more complex hierarchies? Could we develop a multi-level Stackelberg learning approach based on the principles of LSDN?
That's a great question. And it's very relevant because so many real-world systems have those multi-level hierarchies. Think about a supply chain with multiple tiers of suppliers, or a complex organization with different levels of management. Current machine learning methods often struggle to model those kinds of nested dependencies.
Right. And LSDN's ability to disentangle those agent-driven and environment-driven dynamics in a two-player setting, that might be generalizable to these multi-level scenarios, maybe by introducing additional latent spaces or more sophisticated hierarchical versions of the MOGBM. It could allow us to model and learn much more intricate coordination patterns in those large-scale complex systems.
I think that's a really promising direction.
Yeah.
Imagine being able to model the strategic interactions in an entire ecosystem, like a financial market or a political buildscape. That could have huge implications for how we understand and interact with these complex systems.
Absolutely. And even extending LSDN to handle a fixed number of hierarchical levels, that seems like a very achievable research goal in the near future. Developing a truly general framework that can automatically infer and adapt to any number of levels, that's a bigger challenge, but it's a goal worth pursuing. It could revolutionize how we design and control complex multi-agent systems.
It would be like going from choreographing a duet to conducting a whole orchestra. A much bigger challenge, but the potential payoff is enormous.
It is. And just a reminder to our listeners, these are just some of our speculative thoughts on where this research could lead. We encourage you to explore these ideas further and see where your own creativity takes you. If you're interested in diving into the technical details of LSDN, you can find a link to the full paper in the show notes. Thanks for joining us on this deep dive into the fascinating world of imitation learning in Stackelberg Games. We'll catch you next time on The Deep Dive.